When we add a listener to an element, what does the browser actually do? How is the listener able to process an event? And when exactly does this happen? Let's go step by step and see what happens during the processing of an event in the DOM. We'll also look at the internal structure of an event, how it propagates, and how it's handled by the listeners registered on different elements in the DOM. This is Deep Frontend Lore. The first thing to understand is that for a DOM object to receive an event, it must implement the event target interface. For example, the window object implements event target. That's why we can call window add event listener. Unlike the traditional event model based on HTML attributes, such as onClick, the add event listener method doesn't add any property to the element or change its structure in the DOM. When add event listener is called on an element, the event target associated with that element gets a new entry in its internal list of listeners. Where is that list stored? It's managed internally by the browser's engine. Each engine implements it in its own way. But in general, all follow the behavior defined by the DOM standard from the Web Hypertext Application Technology Working Group, Section 2.7, Event Target Interface. Now, to understand how an event propagates and how it's caught by a listener, it's important to know that when an event is dispatched, its flow goes through three main phases: capturing, target, and bubbling. The event interface represents these phases through its event phase property as follows. Phase 0 means the event is not being processed. Phase 1, capturing, means it's moving down toward the target. Phase 2, at target, means it has reached the target node. Phase 3, bubbling, means it's moving back up again. When an event is dispatched, the browser determines a path made up of event target objects. This route is known as the composed path. This path usually includes window as the topmost ancestor and ends at the target itself. If it's an internal event, for example one that occurs inside a shadow root with a composed property set to false, the path is limited to that specific composed tree. The composed path method of the event interface returns it as an array of event target objects. In phase 1, called the capturing phase, the event travels downward from the top node to the target node. When the event reaches the target, phase 2 begins, the target phase. Immediately afterward, the event travels back up along the composed path in reverse order, reaching each ancestor node again. This is phase 3, the bubbling phase. This final phase depends on the bubbles property of the event object. If bubbles is set to false, the event stops after the target phase. Let's look at a simple example. User clicks on a button element. In this case, the event is dispatched and its target is the button that was clicked. When the event reaches the target node, that is, during phase 2, if the element has a listener registered for the click event, that listener's callback is executed. Depending on the properties of the event and how the listener was defined, the same event might also be processed by other listeners along the composed path, either during the capturing phase, before reaching the target, or during the bubbling phase as the event moves back up. Now think about an element that isn't the target of the event but is still part of the composed path. For example, the parent element of the button, which also has a listener registered. Each listener has an internal capture flag that's set to false by default. If you register the listener with capture true, then when the event passes through that element during the capturing phase as it moves down toward the target, the listener processes the event and runs its callback. However, when capture is set to true, that listener won't process the event during the bubbling phase. To sum it up, when capture is set to true, the listener runs during the capturing phase, but not during bubbling. When capture is false, it runs during the bubbling phase, but not during capturing. Now that we understand the path, we must ask, can we control this flow? What if a listener needs to prevent the event from continuing its journey? This is achieved by calling the stopPropagation method on the event object. When a listener invokes event.stopPropagation, an internal stopPropagation flag is set on the event object. This flag instructs the browser's event dispatch mechanism to halt the event's travel to any further event target objects. It is a common misconception that stopPropagation only affects the bubbling phase. This is incorrect. If stopPropagation is called during the capturing phase, it not only stops the event from traveling further down the path, but it also prevents the target phase and the entire bubbling phase from ever occurring. If stopPropagation is called during the bubbling phase, it simply stops the event from bubbling up to the next ancestor. But this stopPropagation method presents a new, more subtle question. What happens if multiple listeners are registered for the same event on the same element? For example, button add event listener click listener own and button add event listener click listener 2. When the click event reaches the button, the browser consults its internal event listener list for that element. According to the DOM standard, listeners are invoked sequentially in the order they were registered. In this case, listener own will run, followed by listener 2. The stopPropagation will not prevent listener 2 from running. It only prevents the event from moving to the next event target. This is where stopImmediatePropagation comes in. This method does two things. First, it sets the stopPropagation flag, just like stopPropagation, but it also sets an internal stopImmediatePropagation flag. This second flag instructs the browser to not invoke any further listeners registered on the same event target for the current event. If listener own were to call event.stopImmediatePropagation, listener 2 would never be executed. This brings us to a crucial and often confused distinction. We must separate the idea of event propagation from the browser's default action. Many events have a native browser behavior associated with them. When you submit a form, the page reloads. When you use the mouse wheel, the page scrolls. The preventDefault method is used to stop this default action. It has no effect on event propagation. An event's propagation can be stopped, but its default action can still occur. Conversely, a default action can be prevented, but the event can still propagate all the way up to the window. There are two key properties related to this. Event.cancelable, a Boolean that is true only if the event's default action can be prevented. Not all events are cancelable, for example, the focus event. Event.defaultPrevented, a Boolean that returns true if preventDefault has already been called on the event. But, as you might guess, this very relationship between listeners and preventDefault created a significant performance problem, especially for touch and scroll events. When a user scrolls, triggering a wheel or touch start event, the browser's rendering thread had to wait for the JavaScript thread to finish executing the listener, just in case that listener might call preventDefault. This waiting period is what causes scroll jank. To solve this, the passive true option was introduced for add event listener. This is a contract with the browser. It signals that the listener promises it will not call preventDefault. This allows the browser to perform the default action like scrolling on a separate thread immediately, without being blocked by the listener's execution. This is critical for maintaining a smooth user experience. If a passive listener does attempt to call preventDefault, the call is ignored, and a warning is often logged to the console. We'll wrap up this investigation here. There's still much more to uncover about how events work, and we'll get to that in the future. Thanks for joining us. This was Deep Frontend Lore. Our purpose is to understand the mechanisms that make the front end possible. We stay rigorously technical, but that doesn't make it any less interesting or enjoyable. You're welcome here even if you just came to have a good time. If you want to truly master front-end and understand how and why things work, you'll need to go beyond conventional articles and tutorials. Deep Frontend Lore will provide you with starting points for your own investigations. Come back and tell us what you've discovered.